Hi, and welcome to this short demo where I'm going to show Polygonica's healing used on terrain meshes that have come from LIDAR data. So first of all, just mentioning this graphical user interface is just a demo program. It's not available for sale. Polygonica is a software library and it's licensed on that basis. Okay, so I'm just going to load this mesh in. So this is a representation of an open pit mine, open cast mine that we've created ourselves. So we've got lots of this data for testing, but we aren't allowed to show it to anyone because it's based on real mines. So this is just our kind of our mock-up, if you like. And you can see we've added random vertex noise, which is more obvious on this bit that's supposed to be planar. And then we've got these interesting colors. So the green lines show edges in the mesh that only have one polygon or face or triangle attached to them, so they're open edges, and you can see there's holes, and you'd expect this kind of thing in a mesh created from a LIDAR scan. But there's also cracks here where the mesh isn't joined together. So if you look at these two triangles, they're not actually joined along that edge. There's no connection there, and there's a gap, and that needs to be fixed. Also interesting, we've got these red and purple patches, which if I just turn on both sides of the graphics, which are on both sides of the surface. I mean, it's a single valued surface here. There's no thickness to it. So the red indicates that the polygons are self-intersecting, and the purple indicates that they are non-manifold. In our terminology, non-manifold is an edge with three or more connections. So these are clearly a bit weird, and they clearly shouldn't be there. So we've got two ways we could start. I think if this was a real mesh, I would probably start by removing all the noise shells, which is removing all the floating disconnected shells that are not connected to the main mesh or are only connected via non-manifold edges or non-manifold vertices. And if we look on the right here, we can see there's around 8,000 of those, which is a lot. That's this clearly should be a single connected mesh, and it isn't. But what just so I can demonstrate it, I'm going to show you first Polygonica's self-intersection fixing. So that will get rid of these problems here. So I'm going to click that. It's saying solid is open, remove self-intersections anyway. So the self-intersection fixing is more reliable when you have a solid body, because it's clear what is inside and what is outside. With a surface, it can be, if a surface folds over on itself and self-intersects, it could create all kinds of nasty geometry, and it's sometimes hard to determine what's what in those kinds of situations. But here it's pretty straightforward. It's clearly a single surface mesh that doesn't fold back in on itself. So I'll just click that, and there we go. So if I look at that, that's all gone, and we've got nice polygons in this region. So let me turn that off, and I'll do an undo. And okay, so we've got those back, and this time I'm actually going to start with what I would probably do with a real mesh from a LIDAR scan, and that's get rid of all these floating shells. Now there's a risk in doing this, because a floating shell could be something you need, but in most cases on these meshes they're not. And you can change, there's a variety of definitions you can use to decide whether something is big enough, or something is small enough to throw away or big enough to keep, basically. But I'm just going to use our default one here, and we're just going to throw all those away. And now we've got these holes, and we've also got these gaps. Now Polygonica has solid closing and surface closing, and it could heal those using that API, and it would do a perfectly good job. But in fact, typically on surfaces, particularly scanned surfaces, you're more likely to want to use hole filling. So here I can select all the holes, and I just want to get rid of this big one around the edge, because that's not a hole that we need to fill. That's just the external boundary, and you can easily remove that in code just by removing the longest edge. So now we've got a lot of holes that we're going to fill, and I'll just pick smooth. So smooth is a fairly simplistic smooth, creates a smooth hole. We also have much more advanced curvature sensitive features and feature smooth algorithms, but to be honest, they're a sledgehammer to crack a nut, and they do take longer to run, so I'm not going to do those here. These holes are all fairly small, so I'll click fill holes, and there we go. And let me turn the edges off. Now the yellow is a highlight in Polygonica demo, so we've highlighted all the holes, and we could now do further operations like remeshing on these to make the mesh look nice and everything. But if I compare them to the original, you can see, like here for example, it's done a pretty nice job of preserving the curvature. Let's find one with some curvature, maybe over here. See, and let's just get rid of this highlight, so you can see it looks pretty nice hole fill result. I mean, it's not particularly advanced hole filling this, but yeah, it does the job. So now we've got a pretty good mesh. It's still noisy. There still could be non-manifold edges in. We've not done anything to actually try to get rid of non-manifold edges explicitly. This traffic light's, because it's got the open edge on the side, this traffic light's always going to stay non-manifold. I can't see any visually, but I'm going to run anyway just to be safe. Fixed topology with the automatic method, and that will get rid of any non-manifold edges for you, using it automatic basically uses a sort of tier of techniques, and it tries one, then another, then another, to see which one's going to give you the best result basically. And then finally, well, we've still got a sort of noisy result with these edges don't look particularly brilliant, so just as a final flourish, we can do a bit of denoising. So if we watch carefully, I'll click denoise, and magically that becomes, these bottoms becomes the bottom of the pit becomes plainer, and these edges become very clean. Now denoising, you can see here it's done some pretty aggressive smoothing of the noise there. I mean, this works pretty well on this model. If you had real noise from a real LIDAR scanner, it might not work quite as well, but it still does a pretty decent job in most cases. And part of the denoise algorithm is identifying sharp edges and making them sharp, which are, in scans, in meshes reconstruction from scans, edges aren't particularly sharp usually, so this helps with that. So that's the end result basically. We've got a nicely fixed, healed, manifold, with the exception of the open edge surface, and you can then go and use that freely for your booleans or whatever other operations you want to do on it. Okay, you can get in touch with us via the Polygonica website. There's a contact form there. You can find us on LinkedIn, and if you've any questions, please don't hesitate to get in touch. I'd be happy to give you a demo or answer your questions. And otherwise, thanks very much for listening.